Welcome to the Explainer. So today we're diving into a framework from Stanford NLP that is really changing how we build with AI. It's shifting the entire paradigm from, prompting to actual programming.
Oh man, if you've ever spent hours, maybe even days, playing that frustrating game of prompt whack-a-mole, you know this feeling, right? You finally get the perfect output, you run it again, and suddenly, poof, it's complete nonsense. Well, that brittleness is the exact problem this whole new approach aims to solve.
And this right here is the fundamental shift. We're moving away from the brittle art of just crafting these text strings and into a much more robust, reproducible world of programming our language models as if they were actual structured, compilable systems.
So what is this revolutionary approach? Let's get into it and break down what DSPY is really all about. Okay, so DSPY, it stands for Declarative Self-Improving Python. It's this research-driven framework from Stanford that just completely flips the script. Instead of telling a language model how to think with some super complex prompt, you just declare what you want it to do. You set the goal and the framework handles the rest.
Yeah, the best way to think about it is that DSPy acts like a compiler. You write your logic in a high-level language, in this case Python, and DSPy takes that and translates or compiles it into the most effective low-level instructions, which are the prompts themselves. And this makes your system not just powerful, but also portable across all sorts of different language models.
So how does this actually work under the hood? Well, it all boils down to two really fundamental building blocks that you'll use to build your AI programs.
First up, you've got signatures. And these are just beautifully simple. A signature is just a clear, declarative statement of what a task is supposed to do. It's like a contract, It defines the inputs and the outputs, like turn a question into an answer without getting all bogged down in the nitty-gritty details. And second, you have modules. So if the signature is the what, the module is the how. This is where you actually define the reasoning strategy. Do you just want a simple prediction or something more complex, like a chain of thought process? Maybe even a React agent that can use tools. The cool part is you can just plug and play these different modules to fulfill the very same signature.
Okay, so how do these pieces actually come together? This is where the whole self-improving part of DSPy really comes to life. It is all in the compiler.
Right, so the DSP compiler, it's powered by these things called optimizers. You give your program a metric for success, say accuracy or maybe semantic similarity, and just a few examples. And then the optimizer goes to work, automatically testing and generating the best possible prompts to absolutely maximize that metric. It basically teaches the language model how to perform your specific task.
This workflow just illustrates the power perfectly. You write your modular program, you provide a data set and a metric to kind of bootstrap the learning, you hit compile, and then you deploy a totally optimized pipeline. It transforms prompt engineering from this messy guesswork into a systematic, repeatable engineering process. It's awesome.
In the results, they're just staggering. In one case study on really complex math word problems, a simple, unoptimized program, it only scored a 33%. But after being compiled by DSP, with no manual prompt changes, mind you, its quality just skyrocketed to 82%. That is a massive leap in performance, and it was all achieved automatically.
Okay, this all sounds fantastic in theory, but what does it actually look like in practice? Let's take a look at some real-world code and see how it stacks up.
So take a look at this. This is a complete system for retrieval augmented generation, or RAG, written in just a few lines of Python. Now, RAG is a super common technique where you first retrieve relevant documents, and then you use those documents as context for the AI to generate an answer. And as you can see, the code just defines a retrieve step and a generate_answer step. It's clean, it's modular, and every single part of this can be automatically optimized by the compiler. It's just readable, maintainable, and incredibly powerful.
So a big question is, how does this fit in with tools we already know, like LangChain? Well, this table lays it out pretty perfectly. You see, LangChain is fantastic for orchestration, for connecting all the different pieces and integrations. DSPy, on the other hand, is focused on optimization, making sure the reasoning steps inside those pieces are as reliable and as effective as they can possibly be.
DSPy really starts to shine when you're building those complex multi-step systems. Think about multi-hop question answering, or really sophisticated agents. In those kinds of pipelines, the failure of just one brittle prompt can derail the entire process. And that is the exact problem that DSPy's automated optimization is designed to solve.
And believe it or not, this is really just the beginning. DSPy is an active research project, and it's constantly pushing the boundaries of what's even possible with this declarative programmatic approach to AI.
I mean, cutting-edge research is leading to even more powerful optimizers and modules. You have techniques like GEPA, which are finding these new ways for prompts to evolve and reflect on their own performance. And then there are concepts like recursive language models, or RLMs, which some folks are calling the AI paradigm for 2026, and they're being built on these same declarative principles, allowing models to programmatically break down complex problems all on their own.
So, this brings us to the final and I think crucial question. In the work that you're doing, is that endless, frustrating cycle of manual prompt tuning and fixing these brittle prompts, is it limiting what your AI systems can truly achieve? Because DSPs suggest there's a much better, more systematic way forward. Thanks for watching.